ladies and gentlemen. How are you guys doing? Can everyone hear me?
Yes.
Awesome. So for today's lecture, we are going to talk about atoms and spectra. So last week we started talking about a little bit about light and frequencies, the electromagnetic spectrum, how optical telescopes work, how radio telescopes work, and we also, I think I ended off last week with the LIGO Observatory. So for today, there's a quick 3 different videos I want to show you. The first one will be about LIGO, the second one about tides that we already talked about, and then the last one about atoms and spectra. So let's begin.
Here's a ridiculous idea. Imagine I snapped a twig in an isolated forest. Then a listener on the opposite side of the planet hears the sound vibrations created by the snap, and just by hearing it, can tell you exactly where I was, at what time I snapped it, and even what kind of tree the twig came from. Of course, this is impossible, but what if I told you that human beings could do something similar, but even more impressive? Instead of a snapped twig, the source of the vibration is a violent event in space, an event that we can detect here on Earth, even though it occurred billions of light years away and billions of years in the past. All we had to do was build one of the largest and most sensitive devices ever created, the Laser Interferometer Gravitational Wave Observatory, LIGO. I'm driving alongside one of the 4-kilometer-long arms of LIGO, the first ever observatory to observe gravitational waves. The arm is so long that they actually had to correct for the curvature of the Earth. And we're about to go inside to the facility to see all the instrumentation. I am so excited. We're getting on some of our clean room garb. This is a class 10,000 clean room. There's more classes, but this is pretty clean. This is cool. So this is like laser starts over there, then there's mirrors here, beam splitter, laser splits. We've got the arm going this way, another arm going that way.
It's all in this room.
So this is like the brain, the guts, this is everything. Up until extremely recently, astronomy was based almost exclusively on studying light. But LIGO is not like other observatories. It's blind. It senses no part of the electromagnetic spectrum like visible light, microwaves, radio waves. Instead, it detects gravitational waves, which are a completely separate phenomenon from light. In 1916, when Albert Einstein published his theory of general relativity, he predicted that masses accelerating in space would create ripples in the fabric of space-time itself. For decades, no one knew if these ripples, called gravitational waves, actually existed. But 99 years later, in 2015, the LIGO team finally sensed a series of extremely tiny vibrations, 1,000th the width of a proton. To get to that level of sensitivity, they needed to create an observatory that was unlike anything else on Earth. Rather than pointing a mirrored sensor at the stars, they built this L-shaped detector with 2 4-kilometer-long vacuum tubes. The arms are covered in concrete, so they're completely protected from all the elements. Then they use lasers and mirrors to detect the compression of gravity with special suspensions that actively cancel out any vibrations generated from activity on the Earth. And they needed to build 2 of them, 3,000 kilometers apart, to operate in complete coordination, because a random vibration at one location could create a false signal that looks like a gravitational wave, but isn't. If a detection is made at both places, you eliminate the possibility of it just being a local disturbance.
The beam splitter itself is in this large chamber right here.
Oh, cool.
But part of the reason why that's so large as well is not just the mirror,
Yeah.
but you've got it in that quad suspension system. And that quad suspension system is really where the magic is in reducing the ground vibrations. Because if you don't reduce those ground vibrations, you don't make detections.
And you have that quad suspension system on
the 4 main mirrors, as well as the beam splitter. So the 5 largest optics that we have, that is in those suspension systems. We really say every vibration bothers us, and we mean it. From the thermal effects on the mirrors, to earthquakes in Australia, they all can cause us problems.
After months of analysis, scientists confirmed that the vibrations detected in 2015 were the signature of two black holes merging. It was a violent event that had occurred 1.3 billion light years away and 1.3 billion years in the past. It also confirmed that an entirely new type of astronomy was possible. Wow, so this is it.
Those are where the lasers exit the enclosure area and go directly into the vacuum system.
Wow. There are laser beams going through these tubes?
Yes.
That is very exciting. They're in infrared though, so we would not even be able to see them if there were no protective tubes there, but still. There's this laser beam that comes out and it's a bit messy. It's got different sort of spatial patterns, and they clean it before it gets sent out into the arms. But then you're telling me now that they also clean the input that comes back in, or the output is what you call
absolutely.
it. Yeah.
So you're getting rid of the patterns of the light you don't want.
Right.
And then you do that before it goes in, and you also do that on the way back out. So yeah, the light comes back in, recombines, and then it goes down here for detection.
And then detection happens over here.
Down here.
So this part that we're going to walk up to, this is where the detection happens.
Yeah. I hate to say where the magic happened because the magic happens all over, but this is where the actual detections are made.
This is amazing. You have to see this. The beam makes it here where you've got the detector. That's where the detection happens.
And I actually have the photodiode in my office that saw the first gravitational wave ever, GW150914.
How did you get that?
Well, because I have to put it out.
So we're putting goggles on to protect from the infrared laser, which you wouldn't be able to see, but you would be able to feel it. LIGO is allowing researchers to explore areas of the universe that were previously hidden because their energy is emitted by objects that are inherently dark, like the collision of black holes. We now know that over millions of pairs of black holes revolve around each other in binary systems. As they orbit, these pairs emit gravitational waves, which removes some of the system's energy and forces the pair to rotate faster and closer together. But because this energy isn't released as light, prior to the detection of gravitational waves, we were never able to observe them, and the very existence of such black hole binaries was contested. But perhaps the most exciting use of gravitational wave detection is yet to come. In the very first moments of the universe, the electromagnetic force and the weak nuclear force, two of the fundamental forces of the universe, were indistinguishable. But when those forces separated, they're believed to have produced gravitational waves. And unlike light waves, gravitational waves interact extremely weakly with matter. So much so that gravitational waves could still be traveling from a time when the universe was a billionth of a billionth of a billionth of a billionth of a second old. If we can build a detector with enough sensitivity to observe these waves, they might give us some information about the very first moments of our universe, which is very exciting. And while this degree of accuracy might be far off, the stunning success of LIGO so far has empowered the advancement of bigger, more sensitive gravitational wave detectors around the world and even in space. Ultimately, gravitational waves tell us how stars live and die. They give us insight into the lifespan of ravenous black holes, and they may reveal what happened at the very beginning of time. Gravitational waves are a profound expansion of our human senses, broadening our vision and bringing us one step closer to understanding the inner workings of the universe. Now that you know all about gravitational waves, keep watching as Joe Hansen explores how scientists created humanity's first image of a black hole with a telescope the size of the Earth. Thank you to Draper and its Hack the Moon initiative for supporting PBS Digital Studios. You know the story of the astronauts who landed on the moon. Now you can log on to wehackthemoon.com to discover the story of the male and female engineers who guided them there and back safely. Hack the Moon chronicles the engineers and technologies behind the Apollo missions. Brought to you by Draper, the site is full of images, videos, and stories about the people who hacked the moon. PBS is bringing you the universe with the Summer of Space, which includes 6 incredible new science and history shows airing on PBS and streaming on pbs.org and the PBS video app. Watch it all on PBS.
You know, if Shakespeare had been an astronomer, he'd have said that there is a tide in the affairs of the universe, and on such a full sea are we now afloat? He would have been right. You might just think of tides as the ocean going in and out every day. But in fact, what astronomers call tides are a subtle but inexorable force that have literally shaped most objects in the universe. And to understand tides, we start with gravity. Gravity is a force, and it weakens with distance. An important thing to note is that we measure gravity from the center of mass of an object, not its surface. One way to think of the center of mass of an object is the average position in an object of all its mass. For an evenly distributed sphere, that's its center. Right now, unless you're an astronaut, you're about 6,400 kilometers from the center of the Earth. If you stand up, your head is a couple of meters farther away from the Earth's center than your feet. Since gravity weakens with distance, the force of Earth's gravity on your head is an eensy-weensy bit less than it is on your feet. How much less? A mere 0.00005%. And that's way too small for you ever to notice. But what if you were taller? Well, the taller you are, the farther your head is from the Earth's center and the weaker force it will feel. If you were, say, about 300 kilometers tall, the force of gravity would drop by about 10% at your head. That probably would be enough to notice if you weren't dying from asphyxiation and, being 300 kilometers tall. This change in the force of gravity over distance is what astronomers call the tidal force. When you have a massive object affecting another object with its gravity, its tidal force depends on several factors. For one thing, it depends on how strong the gravity is from the first object. The stronger the force of gravity, the stronger the tidal force will be on the affected object. It also depends on how wide the affected object is. The wider it is, the more the force of gravity from the first object changes across it, and the bigger the tidal force. Finally, it depends on how far the affected object is from the first object. The farther away the affected object is, the lower the tidal force will be. Tides depend on gravity, and if gravity is weaker, so is the tidal force. The overall effect of the tidal force is to stretch an object. You're applying a stronger force on one end than you are on the other, so you're pulling harder on one end. That'll stretch it. And this is where tidal forces become very important. Look at the moon. It has gravity, but much less than the Earth because it's less massive. It's 380,000 kilometers away, so the gravitational force it has on you is pretty small. And you're pretty small compared to that distance, just a couple of meters long from head to feet. But the Earth is big. It's nearly 13,000 kilometers across. That means the side of the Earth facing the moon is about 13,000 kilometers closer to the moon than the other side of the Earth. This is a pretty big distance, enough for tides to become important. The side of the Earth facing the moon is pulled harder by the moon than the other side of the Earth, so the Earth stretches. It becomes ever so slightly football-shaped, like a sphere with two bulges, one pointing toward the moon and one pointing away. This is probably the weirdest thing about tidal forces. You might expect only one bulge on the side of the Earth facing the moon. But remember, we measure gravity from the centers of objects. The side of the Earth facing the moon feels a stronger pull toward the moon than the Earth's center, so it's pulled away from the center. But the side facing away from the moon feels a weaker force toward the moon than the Earth's center. This means the center of the Earth is being pulled away from the far side. This is exactly the same as if the far side is being pulled away from the center. And that's why you get two bulges on opposite sides of the Earth. The tidal force is therefore strongest on the sides of the Earth facing toward and away from the moon, and weakest halfway in between them on each side. A lot of the Earth is covered in water, and water responds to this changing force, this stretching. The water bulges up where the tidal force is strongest on opposite sides of the Earth. If there's a beach on one of those spots, the water will cover it, and we say it's high tide. If a beach is where the tidal force is low, the water's been pulled away from it, and it's low tide. But wait a second. The Earth is spinning. If you're on a part of the Earth facing the moon, you're at high tide. 6 hours later, a quarter of a day, the Earth's rotation has swept you around to the spot where it's low tide. 6 hours after that, you're at high tide again, and then another 6 hours later, you're at low tide for the second time that day. Finally, a day after you started, you're back at high tide once more. And that's why we have 2 high tides and 2 low tides every day. Very generally speaking, the ocean tide causes the sea level to rise and fall by a meter or 2 every day. Incidentally, the solid Earth can bulge as well. It's not as fluid as water, but it can move. The tidal force stretches the solid Earth by about 30 centimeters. If you just say you move up and down by about that much, twice. Like the saying goes, a rising tide lifts all surfaces. The Earth's spin has another effect. Lag in the water flow means the water can't respond instantly to the tidal force from the moon. The Earth's spin actually sweeps the bulges forward a bit along the Earth. So picture this. The bulge nearest the moon is actually a bit ahead of the Earth-Moon line. That bulge has mass, Not a lot, but some. Since it has mass, it has gravity, and that pulls on the moon. It pulls the moon forward in its orbit a bit, like pulling on a dog's leash, accelerating it. The moon responds to this tug by going into a higher orbit. The moon is actually moving away from the Earth. The rate of recession of the moon has been measured, and it's something like a few centimeters per year, roughly the same speed your fingernails grow. Now get this, the moon has gravity. Just as the bulge is pulling the moon ahead, the moon is pulling the bulge back, slowing it down. Because of friction with the rest of the Earth, this slowing of the bulge is actually slowing the rotation of the Earth itself, making the day longer. The effect is small, but again, it's measurable. Okay, let's get a little change of perspective. Everything I've said about the moon's tidal effect on the Earth works the other way too. The moon feels tides from the Earth, and they're pretty strong because the Earth is more massive and has more gravity than the moon. Just like Earth, there are two tidal bulges on the moon, one facing the Earth and one facing away. Long ago, the moon was closer to the Earth and spinning rapidly. The moon's tidal bulges didn't align with the Earth, and the Earth's gravity tugged on them, slowing the moon's spin and moving it farther away. As it moved farther away, the time it took to orbit once around the Earth increased. Its orbital period got longer. Eventually, the lengthening rotation of the moon matched how long it took to go around the Earth. When that happened, the axis of the bulges pointed right at the Earth. That's why the moon only shows one face to us. It spins once per month and goes around us once per month. If it didn't spin at all over that month, we'd see the entire lunar surface. But since it does spin once per orbit, we only ever see one face. This is called tidal locking, and it's worked on nearly every big moon in the solar system. Tides from their home planet have matched their spin and orbital period. These moons all show the same face toward their planet. Now wait a second. If the moon has gravity, which causes tides, and is the root cause behind all these shenanigans, what about the sun? It's even bigger than the moon. Tides depend on the gravity from an object and your distance from it. The sun is far more massive than the moon, but much farther away. These two effects largely cancel each other out. And when you do the math, you find the sun's tidal force on the Earth is just about half that of the moon's. The way the sun's tidal force and the moon's tidal force interact on Earth depends on their geometry, which changes as the moon orbits us. At new moon, the Earth, moon, and sun are in a line. The moon's tidal force aligns with the sun's, reinforcing it. This means we get an extra high tide and an extra low tide on Earth. We call this the spring tide. When the moon is at first quarter, the tidal bulge from the moon is 90 degrees around from the sun's. High tide from the moon overlaps low tide from the sun. We get a slightly lower high tide and a slightly higher low tide. We call those neap tides. The pattern repeats when the moon is full. The moon, Earth, and sun fall along a line again, and we get spring tides. A week later, the moon is moved around, and we get neap tides again. Not only that, the moon orbits the Earth on an ellipse. When it's closest to us, we feel a stronger effect. If that also happens at new or full moon, we get an added kick to the spring tides. This is called the Proxygian tide and can lead to flooding in low-lying areas. Unless you live on the coast, I bet you had no idea tides were so complex. Tides are universal. They work wherever there's gravity. If two stars orbit each other, each raises a tide in the other. Just like the Earth and Moon, that can slow their spin and increase their separation. Many planets orbiting other stars may be tidally locked to those stars. Near a black hole, where the gravity is incredibly intense, the tides are so strong they would pull you like taffy into a long, thin string. Astronomers call this effect spaghettification. No, seriously, that's what we call it. Today you learn that tides Hey, Phil Plait here, and this is Crash Course Astronomy. In last week's episode, I mentioned that nearly all the information we have about the universe comes in the form of light. But how does that light get made? What can it tell us about these astronomical objects? And honestly, what is light? Here's a hint. Light is a wave. It took centuries of thought and experiments to figure that out, and to also figure out that, at its most basic, light is a form of energy. It travels in waves, similar to waves of water in the ocean. Except with light, the things doing the waving are electric and magnetic fields. Literally, light is a self-contained little bundle of these two fields intertwined. That's why we call light electromagnetic radiation. The details of this are very complex, but we can make some pretty good overall observations about light just from thinking of it as a wave. If you're floating in the ocean, you'll move up as a wave passes you, then back down, then back up again when the next wave rolls by. The distance between these crests in the wave is called the wavelength. Since light is a wave, it has a wavelength as well, and this may be its single most important feature. That's because the energy of light is tied to its wavelength. Light with a shorter wavelength has more energy, and light with a longer wavelength has less energy. And our eyes have a really convenient way of detecting these different energies. Color. What you think of as the color violet is actually light hitting your eye that has a short wavelength. Red light has a longer wavelength, about twice the distance between crests as violet light. All the colors in between, orange, yellow, green, blue, have intermediate wavelengths. This spread of colors, wavelengths, is called a spectrum. Over millions of years, our eyes have evolved to detect the kind of light the sun emits most strongly. Well, that makes sense. That makes it easier for us to see. We call this kind of light visible light. But that's just the narrowest sampling of all the different wavelengths light can have. If light has a slightly shorter wavelength than what our eyes can see, it's invisible to us, but it's still real. We call that ultraviolet light. Light with shorter wavelengths than that fall into the X-ray part of the spectrum, and light waves with the shortest wavelengths of all are called gamma rays. At the other end, light with slightly longer wavelengths than the reddest color we can see is called infrared light. Light waves longer than that are called microwaves, and those with the longest wavelengths of all are called radio waves. These different groups don't really have hard and fast definitions. Just think of them as general guidelines. But together, we call all of these different kinds of light the electromagnetic, or EM, spectrum. And remember, energy goes up when the wavelength gets shorter. So ultraviolet light has a higher energy than violet, X-rays have a higher energy than that, and gamma rays have the highest energy of all. Infrared light has lower energy than red light, microwaves lower than that, and radio waves have the lowest energy. When you look at the whole EM spectrum, you'll probably notice that we really do only see a teeny little sliver of it. Most of the universe is invisible to our eyes. That's why we build different kinds of telescopes, to detect the kind of light our eyes can't detect. They let us see a lot of stuff that otherwise we'd never notice. So you might be asking, how is light made? Well, one of the most basic properties of matter is that when you heat it up, it gains energy, and then it tries to get rid of that energy. Since light is energy, one way to get rid of energy is to emit light. Another important property of matter is that the kind of light an object emits depends on its temperature. An object that's hotter will emit light with a higher energy, that is, a shorter wavelength. Cooler objects give off light with a longer wavelength. You may have seen this in action. Heat up an iron bar and it starts to glow red, then orange, then yellow as it gets hotter. The color, the wavelength of light emitted, changes as the bar heats up. Astronomers use a shorthand for this. We say that light with a shorter wavelength is bluer and light with a longer wavelength is redder. Don't take this literally. We don't really mean more blue or more red, just that the wavelengths are decreasing or increasing. So in this lingo, ultraviolet light is bluer than blue and X-rays are bluer than ultraviolet. So objects that are more energetic, that have a higher temperature, are bluer than cooler, redder objects. This rule of thumb works really well for dense objects like iron bars and stars. Even humans. You emit light, but it's in the far infrared, well beyond what our eyes can see. There are less dense objects in space too, like gas clouds, and the way they emit light is different. To understand that, we have to zoom in on them, way, way in, and look at their individual atoms. And to understand that, we need to take a brief diversion into atomic structure. Atoms are the building blocks of matter. In general, atoms are made up of 3 subatomic particles: protons, neutrons, and electrons. Protons have a positive electric charge, electrons a negative charge, and neutrons are neutral. Protons and neutrons are much more massive than electrons and occupy the centers of atoms in what's called the nucleus. Electrons whiz around the nucleus, their negative charge attracted by the proton's positive charge. The type of atom depends on how many protons it has in the nucleus. Hydrogen has 1 proton, helium 2, lithium 3, and so on up the periodic table of elements. It's common to think of the electron as orbiting the nucleus, like a planet orbits the sun, but that's not really the case. The real situation is fiendishly complex and involves pretty hairy quantum mechanics, but in the end, The electron is only allowed to occupy very specific volumes of space around the nucleus, and those depend on the electron's energy. Think of these like stairs on a staircase, where the landing is the nucleus. When you walk up the stairs, you have to use energy to go up, and when you do, you have to go up a whole step at a time. If you don't have the energy to get to the next step, you can't move. You can be on the first step or the second step, but you can't be on the first and a half step. There isn't one. Electrons are the same way. They whiz around the nucleus with a very discrete amount of energy. If you give them an additional precise amount of energy, they'll move up to the next energy level, the next step. But if you give them the wrong amount, they'll just sit there. The opposite is true as well. Electrons can be in a higher energy state, up on a higher step, and then give off energy when they jump down. The amount they give off is exactly the same amount needed to get them to jump up in the first place. How do they get this energy? Light. If light hitting the atom has just the right amount of energy, the electron will absorb it and jump up. It can also jump down and emit light at that energy too. An electron can also jump 2 steps or 3 or whatever, but it needs exactly the right energy to do it. But as I said earlier, energy and wavelength are the same thing, and that's equivalent to color. So when an electron jumps up or down, it absorbs or emits a very specific color of light. Not only that, but the steps are different for different atoms. To stick with our analogy, it's like different atoms are different staircases with different heights between the steps. So when an electron jumps down a step in a hydrogen atom, it emits a different energy, a different color of light, than an electron jumping down in a helium or calcium atom. And this is the key to the universe. Because different atoms emit different colors of light. If we can measure that light, in principle, we can determine what an object is made of, even if we can't touch it, even if it's a bazillion light years away. And we can. Can you tell the difference between these two squares? They're a very slightly different shade of red. Your eye probably can't tell the difference, but a spectrometer can. This is a device that can precisely measure the wavelength of light and can, for example, distinguish light emitted by a hydrogen atom from light emitted by helium. When you hook one of these spectrometers up to a telescope, you can figure out what astronomical objects are made of. In the case of thin gas clouds in space, the atoms are basically floating free, rarely bumping into one another. The atoms emit those individual colors of light, allowing us to identify them. Unlike dense stars, the color of the thinner gas depends more on what's in it than its temperature. And this is how we learned what the universe is made of. Stars and gas clouds in space are mostly hydrogen, with some helium and heavier elements thrown in. Jupiter has methane in its atmosphere, Venus carbon dioxide. Everything in the universe has its own mix of ingredients, like cakes at a bakery. With spectroscopy, we can taste them. But wait, there's more. You're probably familiar with the Doppler effect, the change in pitch when, say, a motorcycle goes by. In sound, the wavelength defines the pitch. Higher tones have shorter wavelengths and lower tones longer wavelengths. When the motorcycle is headed toward you, the sound waves get compressed, causing the pitch to rise. After it passes you, the pitch drops because the wavelengths get stretched out. The same thing happens with light. If an object is headed toward you, the wavelength of light from the source gets compressed, shorter. We say the light is blue shifted. If it heads away, the wavelength gets longer and it's red shifted. Apply that to a spectrum, and by measuring that shift, we can tell if an object is moving toward or away from us. Here's a teaser. This becomes super important later when we talk about galaxies. Spoiler alert, the universe is expanding, and it's this redshift that allowed us to figure that out. And that's still not the end of it. With other spectroscopic techniques, we can determine if an object is spinning and how fast, whether it has a magnetic field and how strong it is, and even how massive and dense an object is. A vast amount of the fundamental properties of astronomical objects can be found just by dissecting their light into individual colors. Almost everything we know about the universe comes from the light objects in it give off. Pictures of astronomical objects show us their structure, their beauty, and hint at their history. But with spectra, we can examine their blueprints. Today you learned that light is a form of energy.
So hopefully that answered a few questions that we discussed last week, as well as what we are going to do today. So for today, we're going to discuss what is atoms and spectra, look at their model, their orbits, the interactions of light between matter, the radiation of heated objects, and then finally end off with the Doppler effect. So in the previous chapter, we learned how telescopes work and how telescopes gathered light. Same principle as a camera works. But now we're going to talk about the spectra. So at the end of this lecture, we are going to answer 3 important questions. And those questions are: how do atoms interact with light to produce spectra? What are the types of spectra that we can observe? And then finally, what can you learn from spectra of celestial objects? So in this image, this is how an emission spectrum will usually look like. So in the bottom diagram, we can see our emission lines, and in the bottom top part, we can assign them colors. So when we look at certain elements, this is how an emission spectrum will look like. And then this emission spectrum will be from the object we are investigating. And the spectrum will give us a broad range of information of the spectrum that we are seeing. So the universe is populated with brilliant stars illuminating exotic planets and fabulously beautiful clouds of glowing gas. But beyond the members of our tiny local solar system, they're all out of reach for this foreseeable future. So no human space probe has visited another star, and no telescope can directly examine the insides of any celestial object. The information you can obtain about most of the universe is contained in the light reaching you across space. The earthbound humans knew almost nothing about the composition of celestial objects until the early 19th century. First, the German optician Joseph von Fraunhofer studied the spectrum of the sun and discovered that it's interrupted by more than 600 dark lines, representing colors missing from the sunlight Earth receives. So in these spectrum we see below is what he observed. So here we can see visible light, and here we can see how it increases, and here we can see dips in it, and that is what we called an absorption spectrum. So question for you guys: if I speak about an absorption spectrum and emission spectrum, will you be able to distinguish between them? Awesome. So the other scientists performed laboratory experiments showing that those spectral lines are related to the presence of various atoms in the sun's atmosphere. Finally, astronomers observed that a spectra of other stars has similar patterns of lines, which opened a window to real understanding of how the sun and stars are related. The atom. So first thing, let's talk about an atom. So you're probably all familiar with this diagram of an atom, right? Awesome. So this is a good representation, but what we will realize is in practice, an atom doesn't really look like this, and I will show you in a moment how we would really represent an atom. To think about how atoms interact with light, you need a working model of an atom. And in this chapter, you will begin your study of atoms by creating a mental model of an atom. Remember that such a model can have practical value without being true. The stars are not actually attached to a sphere surrounding Earth. But to navigate a ship or point a telescope, it is useful to pretend they are. The electrons in an atom are not actually little beads orbiting nucleus the way planets orbit a sun, but for some purposes it is useful to picture them as such. So the model atom contains a positively charged nucleus at its center, which consists of two kinds of particles: protons, which carry a positive electrical charge. Neutrons have no charge. That means the nucleus has a net positive charge. The nucleus of the model atom is surrounded by a cloud of electrons that have low mass particles with negative charges. Normally, the number of electrons equal the number of protons, and the positive and negative charges balance to produce a neutral atom. The single atom is not a massive object. A hydrogen atom, for example, has a mass of only 1.67 times 10 to the power minus 27th kilogram, so about a trillionth of a gram. Protons and neutrons have masses almost 2,000 times greater than that of an electron, so most of the mass of an atom lies in the nucleus. An atom is mostly empty space, and to see this, imagine constructing a simple scale model of a hydrogen atom. Its nucleus is a single proton with a diameter of approximately 1.7 times 10 to the minus 15th of a meter. If you multiply this by 1 trillion, you can represent the nucleus of your model atom with something about 1.7 millimeter diameter. The region of hydrogen atom can contain the electron has a diameter of about 0.2 nanometers. So multiplying by a trillion increases the diameter to about 240 meters. So what this means is, it is a common misconception, and most people, without thinking about it much, imagine that matter is solid. But now you understand that atoms are mostly empty space. And the chair you sit on, the floor you walk on, are mostly not there. So when we represent this, and let's say we can say the nucleus of our atom is the size of a grape, then we can place this on a football field. And this is the size of a football field. Then here we can see where electrons are starting to orbit. And this is just a representation to show how much empty space there actually are inside an atom. So there are over 100 chemical elements, and the number of protons in the nucleus of an atom determines which element it is. For example, a carbon atom has 6 protons in its nucleus. An atom with 1 more than that is nitrogen. An atom with 1 fewer is boron. Although an atom of a given element always has the same number of protons in its nucleus, the number of neutrons is less restricted. For instance, if you add a neutron to a carbon nucleus, it would still be carbon, but it would be slightly heavier. Atoms that have the same number of protons but a different number of neutrons are isotopes. Carbon has 2 stable isotopes. One contains 6 protons and 6 neutrons for a total of 12 particles, and is usually denoted carbon-12. Carbon-13 has 6 protons and 7 neutrons in its nucleus. The number of electrons in an atom of a given element can vary, and protons and neutrons are bound tightly into the nucleus, but electrons are held loosely in the electron cloud. So before I continue, are you guys all happy with what an isotope is? Awesome. So the next thing we need to talk about is ionized atoms. So running a comb through your hair creates a static charge by removing a few electrons from the atoms. And an atom that has lost or gained 1 or more electrons is said to be ionized, is called an ion. A neutral carbon atom has 6 electrons that balance the positive charge of 6 protons in its nucleus. If you ionize the atom by removing 1 or more electron, the atom is left with a net positive charge. Under other circumstances, an atom may capture one or more extra electrons, giving it more negative charges than positive. Such a negative charge atom is also considered an ion. So question, sir, is there something that occupies the empty space, or is it just a vacuum? Do you get dark energy in the space in between the nucleus and the atoms, like how there is dark energy in space? So no, nothing literally occupies. That's just empty space in between the atoms. So it's not a vacuum, because we still, it's so small you can call it a vacuum, but it's not entirely a vacuum. It's just empty space. And no, it's not dark energy in between them. So we will discuss in a later chapter a bit about dark energy. But dark energy isn't between atoms. So what we realize with dark energy is, in a later chapter, we also get dark matter. And dark energy and dark matter are two interesting concepts we will talk about. So another question. So, sir, does a neutron increase the mass of an element? Yes, it does. So if you add neutrons, it increases the mass, and if a little bit. So yes, that also happens. Does that answer both of your questions? Awesome. So atoms that collide may form bonds with each other by exchanging or sharing electrons, and two or more atoms bonded together form a molecule. Atoms do collide in stars, but high temperatures cause violent collisions that are unfavorable for chemical bonding. Only in the cooler stars are the collisions gentle enough to permit the formation of chemical bonds. The presence of molecules such as titanium oxide detected in some stars is a clue that stars are very cool compared with other stars. Electrons are bound by the atom by the attraction between the negative charge and a positive charge on the nucleus, and this attraction is known as the Coulomb force. To ionize an atom, you need a certain amount of energy to pull an electron completely away from its nucleus. And this energy is the electron's binding energy, the energy that holds it to the atom. The size of an electron's orbit is related to the energy that binds it to the atom. If an electron orbits close to the nucleus, it is tightly bound, and a large amount of energy is needed to pull it away. In other words, its binding energy is large. An electron orbiting further from the nucleus is held more loosely, and less energy is needed to pull it away. That means it has small binding energy. Nature permits atoms only certain amounts. We call that quanta of binding energy. The laws that describe how atoms behave are called the laws of quantum mechanics. Because atoms can have only certain amounts of binding energy, your model atom can have orbits only of certain sizes called permitted orbits. These are like steps in a staircase. You can stand on number 1 step or number 2 step, but not on a number 1 1/4 step. There isn't one. So the electrons can occupy any permitted orbit, but there are no orbits in between. The arrangement of permitted orbits depends primarily on the charge of the nucleus, which in turn depends on the number of protons. So when we look at these valence orbits, you can be in orbit 1, orbit 2, or orbit 3, but nothing in between. You cannot be on, say, orbit 1.5 or orbit 2.2. There's only the OSIT orbit. So in the video we've watched, we use the analogy of stairs. You can be on step 1, step 2, or step 3, but nothing in between. And that is how electron orbits work. And that is something important to remember. So when we represent our atom, we can see our nucleus with our different shells, or valence orbits is another term. But we cannot be in between them. So we can rather be in orbit 1, orbit 2, orbit 3, but not in between. So like I said, This is usually how we think about an atom, and like the opening slide I showed you. But when we look at an actual atom, this is how we would more accurately and mathematically describe an atom. So in here, we can see the nucleus, we can see electron orbits, and we can see the electric fields as well as the magnetic fields of an atom. So this is more complicated, but this is the mathematically correct way to show a structure of an atom. So everybody's still following. Awesome. So that brings us to the periodic table. So the periodic table each has their own unique set of valence orbits, like I showed you now, and they all have their own unique structure. But this is important for astronomy because we can analyze all of these different elements in a lab. And by analyzing these elements in a lab, we realize what their structure looks like. So, if light and matter did not interact, you would not be able to see these words. In fact, you would not exist, because among other problems, photosynthesis would be impossible. So there would be no grass, wheat, bread, beef, cheeseburgers, or any other kind of food. The interaction of light and matter makes life possible, and it also makes it possible for you to understand the universe. So when I show you this image of light and matter, what do you think that is? And that is an absorption spectra of, almost right, so that is the absorption spectra of the sun currently. So right now, when we look at all those little gaps, so these absorption streaks we are seeing, that corresponds to the chemical composition in our own sun. So that means what elements has already been fused, which is very cool. So each electron orbit in an atom represents a specific amount of binding energy. So physicists commonly refer to the orbits as energy levels. Using this terminology, you can say that an electron is in its smallest and most tightly bound orbit in its lowest permitted energy level, which is called the ground state. And you can move the electron from the energy level to another by supplying enough energy to make up the difference between the two energy levels. It would be like moving a package from a low shelf to a high shelf. The greater the distance between the shelves, the more energy you would need to raise the package. The amount of energy needed to move the electron is the energy difference between the two energy levels. So if you move an electron from a low energy level to a higher energy level, the atom becomes excited. So one way an atom can become excited is by collision. If two atoms collide, one or both may have electrons knocked into a higher energy level. And this happens very commonly in hot gas, where atoms move rapidly and collide often. Another way an atom can become excited is to absorb a photon. As you learned in a previous chapter, a photon is a bundle of electromagnetic waves with specific energy. Only a photon with an exactly the right amount of energy can move the electron from one level to another. And if the photon has too much or too little energy, that atom cannot absorb it. Because the energy of a photon depends on its wavelength, only photons of certain wavelength can be absorbed by any given atom. So when we have this figure, here we can see we have the nucleus, And here we have 2 incoming photons. So if it is the exact amount of energy needed and the electron absorbs it, that electron will move to a higher valence orbit. But one thing that we need to take note, and that we will, which is important, is the electron cannot remain in that orbit indefinitely. It has to release energy again and fall back to the energy level where it comes from. So when it releases that energy in a photon again and then falls back to its original ground state. So question, so if an electron needs energy to move to a higher level, does it release energy to move to a lower level? Yes, that is exactly what happens, and that is very, very important to note. So why can't electron remain in a higher level? So one thing is, if you move to a higher level, then your atom becomes more unstable. And you cannot have an unstable atom. So usually is the atom tries to stabilize itself. And the only way you can stabilize it is by releasing that energy again. And then the electron falls to the lower orbit or the ground state, and then it becomes a more stable atom. So the atoms cannot exist in an excited state forever. An excited atom is unstable and must eventually, usually within 10 to the minus 9th, to the 1.10 to the power that should be minus 6 of a second, give up the energy it has absorbed and return its electron to a lower energy level. This electron in an excited atom tends to tumble down to its lower energy level, the ground state. When the electron drops from a higher to a lower energy level, it moves from a loosely bound level to one that is more tightly bound. The atom then has a surplus of energy, the energy difference between the levels that it can emit as a photon with a wavelength corresponding to that amount of energy. Because each type of an atom or ion has a unique set of energy levels, each type absorbs and emits photons with a unique set of wavelengths. As a result, you can identify the elements in a gas by studying the characteristic wavelengths of light that absorbed or emitted. So question, does that mean that electrons absorbing light from an energy transfer with 100% efficiency? Yes. You can argue that way, but it has to be a specific frequency. If it doesn't have that specific frequency, then it won't absorb. So is it possible that a photon can travel straight through an atom? In other words, just pass through the atom's empty space without being absorbed by any electrons? Yes, that can happen as well. So one thing that's important is that photon needs to hit the electron directly. Otherwise, it'll just miss the electron and it won't be absorbed. So photons are not charged. So here we can see you have our atom with our wavelength. So here it's there. So that's the correct amount of energy. It jumps to our valence orbit and then it releases it again. So are you guys familiar what these types of lights are? Not LED, but those are neon lights. And you guys know how neon lights work? So with your neon lights, and not only neon lights, your normal fluorescent lights as well, has a gas inside. So with your fluorescent lights, you can get it in a cool white and a warm white color. Same with our neon lights, that has a neon gas in, so the element. And you get those neon lights in different colors, so there are different isotopes of them. So what happens is you have the gas, such as neon inside the tube or in your fluorescent tube. You have the gas, and then on both sides of it, so around about in your tube, you will have a electrical current that's usually in the form of a switch mode power supply. So now you send a current through the tube. So that current is at the correct frequency. So now your electrons jumps to higher valence orbit. And once they go back to the ground state, they release a photon that corresponds to the color you are seeing. And that is how those fluorescent light works. Isn't that cool? And does that make sense? Awesome. So just a heads up, when one of these fluorescent tubes breaks, such as the top right corner, just leave the room for a moment, because unfortunately the gas that's in there is toxic to humans and animals. So when we look at the sun, we can actually see three emission spectrums of neon that we can pick up in the sun. So that means the element neon has been fused in the sun already. So by going back a slide, by studying this in a lab, we can see neon in our own sun. And therefore we can determine the chemical composition of our sun. So when we look at different stars, we can see these stars are at different colors. So this is Orion. So the constellation Orion. So here we can see Sirius, here we can see Betelgeuse, but they are all in different colors. So if we zoom into this one, this is an X-ray image. But let me ask you guys a question. Why is some stars different colors than other stars? And not made of different elements and not different gases. It's purely the temperature of that star. Purely the temperature. So the more bluish a star is, the hotter it is. The more yellowish it is, the cooler it is. So now we're going to spend a moment to talk a little bit about that. So the starlight you see comes from gases that make up the visible surface of a star. Its photosphere. So layers of the gas deeper inside a star also emit light, but that light is reabsorbed before it can reach the surface. So the gas above this photosphere is too thin to emit such light. The photosphere is the visible surface of a star because it is dense enough to emit lots of light, but transparent enough to allow light to escape. So we are going to do an entire chapter on the sun itself. But if we characterize the sun, we have the sun, the core. This extension of the sun is the corona. The atmosphere of the sun is called the chromosphere. Then we have the radiation zone, the convection zone, and the photosphere. So blue is hot and yellow is cool. Yes, so the more bluish it is, the more hotter it is. The more yellow it is, the more cool it is. That comes purely from when we look at here on Earth, temperatures as well. So if we have a piece of iron, like in this photograph, we have a horseshoe. What happens when we heat it up and it starts glowing yellowish red? It starts to heat up, right? And that heat up causes it to be yellowish reddish. So what would happen if we would increase the heat even more? It becomes hotter. So right now there's a distinction between, so remember there's a bit of a distinction right here. So it's because blue light needs more energy than yellow light. No, it's nothing to do with that. It's just how it works in nature. So if you heat it up even more, it would start becoming a more whitish, bluish color, which shows it is more hot. Same thing is, if you have a lighter, if you use your lighter or even a candle, what color is if you're closer to the heat source? So the candle, if you go closer to the lint inside, or a lighter, if you go closer to the striker, it is actually more of a whitish color, whitish blue. That is hotter. So if you go on a flame, you go a little bit further out, it got times to cool down a little bit, it becomes more orange, yellowish, reddish. And that's the same thing, it works with stars. So the more hot an object is, the more excited electrons are. Yes, that is exactly it. So when we look at the light from stars and from the glowing horseshoe, it is produced by the acceleration of charged particles. Usually the accelerated particles are electrons because they are the least massive charged particles, and they are on the outside of the atoms. So they are the easiest to get moving. An electron produces a surrounding electric field, and if you disturb an electron, the change in this electric field spreads out at the speed of light as electromagnetic radiation. So the question is, is it possible to make a horseshoe appear blue? Yes, it will. So if you heat it, make it warm enough, it will burn blue or white is the term you can use. As soon as it cools down again, it will become more reddish and then just normal iron. But in this image, it is quite important. Yes, it wouldn't be a horseshoe anymore because it will melt. But yes, you understand the principle. So one thing to take note, if you have moving electrons, that means you have a moving electric field. And if you have a moving electric field, you have a moving magnetic field. And the other way around, if you have magnetic fields, in return, it will induce an electric field again. So you cannot have the one without the other. If you have a magnetic field, you will always have an electric field. And if you have an electric field, you will always have a magnetic field. And these two are 90 degrees perpendicular to one another. So is the color white or blue hotter? The bluer it is, the hotter it is. So the molecules and atoms in any object are in constant motion. And in a hot object, they are more agitated than in a cool object. And you can refer to this agitation as thermal energy. If you touch an object that contains lots of thermal energy, it will feel as hot as thermal energy flows into your fingers. And the flow of thermal energy is called heat. In contrast, temperature refers to the average speed of the particles. So when astronomers refer to the temperature of a star, they're talking about the temperature of the gases in this photosphere. And they express those temperatures on the Kelvin scale. So a question, why do we use Kelvin as the SI unit for temperature? Yes, absolute zero is one thing. So when you look at a Celsius scale or centigrade, minus 273 corresponds to 0 degree Kelvin. And when we put all three together, Celsius, Kelvin, and Fahrenheit, the reason for that is Fahrenheit and Celsius is not a linear scale. So when you look at Celsius, we cannot say 40 degrees Celsius is 2 times warmer than 20 degrees Celsius. And we cannot say 40 degrees Fahrenheit is 2 times warmer than 20 degrees Fahrenheit. Fahrenheit and Celsius are exponential scales. And as I said in one of our lectures, we like things on a linear scale because if it's on a linear scale, it makes more sense. So the Kelvin scale is the only temperature scale which is linear. So in the Kelvin scale, we can say 40 degrees Kelvin is 2 times warmer than 20 degrees Kelvin. But we cannot say that for Fahrenheit and Celsius. So that is why Kelvin is the SI unit for temperature. Does that make sense? Awesome. So now you can understand why an hot object glows, or to put it another way, why an hot object emits photons, so bundles of electromagnetic energy. So the hotter an object is, the more motion there is amongst its particles. And the agitated particles, including electrons, collide with each other. And when electrons accelerate, change their motion, part of the energy is carried away as electromagnetic radiation. And the radiation emitted by the heated object is called black body radiation. So if a perfectly opaque object would be both a perfectly efficient absorber and a perfectly efficient emitter of radiation, at room temperature, such a perfect absorber and emitter would look black, but at high temperatures, it would glow at wavelengths visible to a human eye. And that explains why in astronomy and in physics context, you will see the term black body referring to objects that glow brightly. So when we look at the black body radiation and flux, here we can see a blue star sits at roughly 18,000 Kelvin, a yellow star at 6,000 Kelvin, and a red star at 4,000 Kelvin. So when we start looking at our different steel and how it glows, we can actually see what its temperature is related to how much heat it has, its black body radiation. So here we can see 4,000 Kelvin is reddish, and purple, which is warmer than blue, it's about roughly 7,000 Kelvin. But there's something interesting. You see these graphs has different peaks, and that peaks correspond to the maximum amount of black body radiation it emits and to the color. Does that make sense? Awesome. So if we speak about black body radiation, does that mean a block of ice will have black body radiation? Yes, it will. So this is an infrared image of a block of ice, because ice is not at absolute zero, so minus 270 degrees Celsius. So we're looking in SI units of Kelvin. So this is now much warmer. So when we look at this ice block, here we can see it still has radiating thermal energy, black body radiation, because it's not at absolute zero. Does that make sense? Awesome. So when we look at space, a few of the objects we are observing is just sitting a few degrees above absolute zero. So they can be 1, 2, 3, 4, 5 degrees Kelvin, but they still have radiation, black body radiation, because we can still detect it. So this is just a bit clearer image. Some of you, do you recognize this famous nebula? This is called the Horsehead Nebula because it looks like a horse's head, and that forms part of the bigger Orion Nebula. So this is one of my favorite objects to observe. So when we look at black body radiation, there are two important features we need to understand. And the first one is the hotter an object is, the more black body radiation it emits. So hot objects emit more radiation because their agitated particles collide more often and more violently with each other. That is why glowing coal from a fire emits more total energy than an ice cube of the same size. Then secondly, the second feature of black body radiation is the relationship between the temperature of the object and the wavelengths of the photon it emits. So the wavelength of the photon emitted when a particle collides with an electron depends on the violence of the collision. For example, only a violent collision can produce a short wavelength high energy photon. That electrons in an object have a distribution of speeds. A few move very rapidly and a few move very slowly. But most travel at intermediate speeds. And because electrons with speeds much higher or much lower when the average speeds are rare, extremely violent and extremely gentle collisions don't occur very often. And therefore, very short wavelength and very long wavelength photon emissions are both rare. Consequently, black body radiation is made up of photons with a distribution of wavelengths, with medium wavelengths most common. So the wavelength of intensity, we call that lambda max, is the wavelength at which the object emits the most intense radiation. And note that lambda max does not refer to the maximum wavelength, but a wavelength of the maximum. Are you guys happy or not? Happy with that definition, or are you a bit confused? Okay, so when we look at lambda max, that is the wavelength with the object with the most intense radiation. So the most intense radiation is the medium wavelengths. So where the most occurs. So sometimes we get with that's extreme. That means they are more than a medium, and sometimes the other extreme point they are less than the medium. So in this case, lambda max doesn't mean the total maximum, so one of the extreme points. The lambda max refers to the medium point, and the medium point is where the most radiation will comes from. Are you guys happy with that definition? Awesome. So when we put this into perspective, when we look at an object that it's emitting at 7,000 Kelvin, we can see the lambda max, so where the most intense radiation is coming from, is in the bluish part. That is the top of this curve, and that will be the lambda max. But at 6,000 Kelvin, the lambda max at the top of that peak will correspond to the more greenish part. And at 5,000 Kelvin, that will correspond to more of the reddish part. You guys happy with that definition, that explanation? So does this correspond to the graph with Kelvin on the X and wavelength on the Y? This will be the other way around. So with Kelvin on the Y and wavelength on the X. So I see a no in there. So what that means is, let me get something out to draw with that's not the same color as the graph. This part over here, the maximum, that is the lambda max. So for 7,000 Kelvin, lambda max corresponds to the. For 6,000 Kelvin, that's a bit cooler, yet to the greenish part, and 5,000 Kelvin to the red part. So where the most intensity comes from. So the most intensity is at the peak of this curve. So right about here, here, and here. Does that make sense? Awesome. So the figure shows the intensity of radiation versus wavelength of three objects of different temperatures. The curves are high in the middle and low at either end because the objects emit radiation most intensely at intermediate wavelengths. The total area under each curve is proportional to the total energy emitted. And you can see that the hotter object emits more total energy than a cooler object. And this rule is known as the Stefan-Boltzmann law. So this is something I usually like to ask in the semester test and exam, is what is the Stefan-Boltzmann law? So the Stefan-Boltzmann law is what we've just seen in the graph. And the total area under each curve is proportional to the total energy emitted. That's the only thing you need to know about the Stefan-Boltzmann law. So let's see if I can highlight this. So for the Stefan-Boltzmann law, is the total area under each curve is proportional to the total energy emitted. And that is the Stefan-Boltzmann law. So that means the more hotter the object is, the more total energy it will emit. The cooler object is, the less total energy it will emit. And then a hotter object will have a shorter wavelength of maximum intensity. So the figure this shows how temperature determines the color of a glowing black body radiation. So the hotter object emits more blue light than red, and this looks blue. And the cooler object emits more red than blue, and corresponding looks red. And this is known as Wien's law. So what that means is, if we have our axis, so here we are going this side, we have shorter wavelengths, so let's say lambda S for this a short. And going that way, we have longer wavelengths. So let's say we call that, for example, lambda long. So what that means is, if something is hotter, it will have a shorter wavelength. Sorry, that's just the other way around. So this should be short, and that should be long. So that means when we have blue light over here, or blue will have a shorter wavelength than red, which is a longer wavelength. So that means the shorter wavelength, the more hotter it is. The shorter the wavelength, the more cooler it is. And that is Wien's law. You guys happy with these two definitions? Awesome. So when putting Wien's law into perspective, X-rays has an even shorter wavelength than blue light or blue radiation. So that means X-rays is even hotter than bluish stars, and gamma rays is even hotter than X-rays. So objects with much cooler than stars don't glow at visible wavelengths, but still produce black body radiation. For example, the human body has a temperature of 300 Kelvin and emits black body radiation in the infrared part of the spectrum. So that is why when you go hunting, you use infrared cameras. And when you look at security systems, such as night vision systems and night vision goggles, they look at the infrared part of the spectrum because we as humans and animals, our lambda max is in the infrared part of the spectrum. So when we look at these little suckers, mosquitoes, in what range, what area of the electromagnetic spectrum would you say are they lambda max? Yes, that will also be infrared. And this is actually cool. So this is an image of a simulation of how mosquitoes would see the world. So that means if you are warmer, you will attract more mosquitoes because they will see a lot more intense infrared radiation. So this is another question I can ask for the semester test or the exam. So I can say black body radiation is described by two simple laws that can be expressed in the precise mathematical form. So many objects give off radiation as black bodies that these two laws are important principles in the analysis of light from the universe. Wien's law expresses quantitatively the relation between temperature and wavelength in which a black body radiation radiates the most energy. Its wavelength of maximum intensity is, so it means the hotter it is, the more radiation it is. And this is the formula for that we are going to use. So here, if you have your temperature, we plug in just the temperature at the Kelvin parts, and we know what the wavelength in nanometers are. So that is the wavelength in nanometers for maximum radiation intensity emitted by a black body equals 2.9 million divided by the black body's temperature on the Kelvin scale. And this law is proportional aid in astronomy. For example, a cool star with a temperature of 2,900 Kelvin emits most intensity of wavelength of 1,000 nanometers, which is the near-infrared part of the spectrum. And in contrast, a very hot star with a temperature of 29,000 Kelvin radiates most intensely at a wavelength of 1,000 nanometers, which is the ultraviolet part of the spectrum. So the Stefan-Boltzmann law relates the temperature of a black body to the total radiated energy. It's expressed in units called joules, symbolized by the capital letter J. And the energy of motion of an apple hitting the floor after falling from a table is about 1 joule. So the total radiation in units of joules per second given off by 1 square meter of the surface of the object equals a temperature raised to the 4th power manipulated by a constant number represented by the Greek lowercase sigma, manipulated by the temperature raised to the 4th power. So how does this help you understand stars? Suppose a star the same size as the sun has a surface temperature twice as hot as the sun's surface. Then each square meter of that star radiates not just twice as much energy, but 2 to the 4 or 16 times as much energy. From this law, you can see that a small difference in temperature between 2 stars can produce a large difference in the amount of energy emitted from the star's surface. So the only thing you need to know from this example is this formula and this formula. So just know how to use it. I will give you a formula sheet, but just know how to use it. So when we look at our different spectra, here we can see emission spectra of hydrogen, helium, lithium, oxygen, carbon, and nitrogen. That is all measured in the lab, and which is easy detectable. So, ladies and gentlemen, I think we will call it for today. We will continue this lecture tomorrow afternoon. So thank you for attending this class. I will also upload the recording ASAP. But otherwise, have a wonderful afternoon. Tomorrow's class, unfortunately, will be online again. I will see you in person next week. But otherwise, have a great afternoon, and I will see you all online tomorrow. I will remain active or two if you have a question. Question, sir, can you go back to the slide with all the colors and where there was 7,000 Kelvin for violet light? Yes, I will go back to that slide. It's this slide you're referring to. Okay, I will go to that again now. So just waiting for Jean Bosself. Does this explain the lambda max? Yes, it does. So the lambda max is where the most intense are, and that most intense also corresponds to the average as well. Does that make sense? So do you think you'd write, yes, if you go to last week's announcement, I've provided you with links of all my COVID recordings as well as what I'm recording now. Yes, so the average. So here with lambda max, I'm referring to the average, but not the maximum. Pleasure. So where and when can I consult regarding the moon assignment? Can you please send me an email? Then I will gladly help you and set up a consultation session. So also, definition between emission and absorption spectrum. So let's go back to that slide. So this is emission spectrum. So this color and background that is faded, you can basically leave that out. So emission spectrum, you will see these bright streaks. So we've done that in the opening slide. So let me quickly see if I can jump to that slide. The opening chapter. This is how an emission spectrum would look like. You'll see you have a dark background with all these colors. So in our spectrometer, actually we don't show the colors, we show this graph at the bottom with these peaks. That is an emission spectrum. But the opposite of that will be an absorption spectrum. So you won't have peaks, then you will have dips in our graph such as this. And if you assign colors to it, it will look something like this. Let me quickly just jump to the correct slide. It will look something like this. So here we will see little gaps in the spectrum. So that will be the difference between an emission and absorption spectrum. So is it possible to get links to the YouTube videos of Crash Course? Yes, I will put on a link for that as well. So on slide 19, what is the difference between electron orbit and electron slide? Electron shell. So slide 18, slide 19. Oh, okay. The only thing with that is the electron orbit that we have is your valence orbit they are orbiting in. But you also get electron shells. So the electron shells are, let's go to where would be a correct, yes, here would have the different shells. So here we have a orbit. So the orbits and the shells are almost the same thing. So here we have a orbit. So you have an orbit where there are already electrons in. But if there's no electrons in, we call that an electron shell because there's literally nothing in it yet. So when it jumps over to it, that means now we have a shell, otherwise it's just an empty shell. So here we will have a full electron shell. So you can see you have literally a shell. The best way to describe it, if you have an electron in the orbit, it creates a shell with electromagnetic radiation. So you have your orbit and you have your shell. Does that make a bit more sense? So let's say we could see light in terms of gamma ray energy, and we had a black body radiation diagram of an object, and it glows red. Would that mean that an object still emits large amount of energy? Yes, it does. So what anything what that means is, if we can literally see gamma rays, that is a lot more intense. So that means it has a lot more energy. But yes, if you put it in perspective on black body radiation, yes, you will still have energy, but a lot less. That is how we can put, for example, a star and an ice cube on the same scale with temperature. Yes, a star is a couple of trillion times hotter than an ice cube, but yes, both of them still emits radiation in the form of black body radiation. I hope that answers your question. Awesome. Did I catch everyone's questions? It seems so. Awesome, guys. Then I'm also going to log off. If you want to set up a consultation session with me, just please send me an email. Otherwise, have a wonderful afternoon and evening, and I'll see you all tomorrow.